Okay. I know that this week, of course, you have a test going on that's due on Fridays. You've had a number of people have already taken it. Once all the tests are finished, so after the deadline passes, over a weekend, I will be examining all of the tests to see if any partial credit can be given. So certainly by Monday, you'll be able to go into My Labs or Canvas and see what your actual. So so what do you see? That is only a lower bound. Okay. In the meantime, I'm going to continue by getting to the new chapter, chapter 3, which is all about determinants of a matrix. And so we're just going to cover a few sections from this chapter. And so your next homework assignment will be due a week from tomorrow. So on the 29th, the homework for this section 3.1 that I'm covering today will be due. All right. Okay. Let's see. Now we've seen a little bit about determinants so far, like for a very simple case, like a 2x2 matrix. But now we're going to get into it for general matrices and learn about their properties and also some applications of determinants. We're going to see one geometric application today. So for a general definition of a matrix, of a determinant, it only is defined for square matrices. So we have an n by n matrix A, and so a definition of the determinant is given by this formula here. Now this formula requires some deciphering so that you can carry it out for a given matrix. So what you do here is notice I have this index I, which is any row index between 1 and n. So you can, in other words, you can choose. And what you do is once you pick your row, for example, maybe the first row, you go along that row and you take each element from that row, so that's Aij here, and you multiply it by this expression, which is called a cofactor. Now, what is a cofactor? You take the submatrix of A as obtained by deleting row I and column J. And then you work out the determinant of that. So in other words, any determinant of an n by n matrix is expressed in terms of determinants of slightly smaller matrices, n by n minus 1 by n minus 1. And then you have to give it the correct sign. So if you're deleting row I column J to get this matrix, then you're going to multiply that by -1 to the I plus J, whatever I plus J are. And that is what is multiplied of Aij here. So you're going along a row and multiplying each element of that row by determinants of a matrix 1 row and 1 column less, and then giving it the correct sign. Now, as I work through examples, I'll be able to explain how you're actually working with this formula in a way that is easier to retain. So when we choose a row to do this, we're using a cofactor expansion across whatever row I that we choose. Now, the typical thing is simply to choose the first row. But sometimes there can be an advantage to choosing a different row simply because, like, what if you have a row where most of the entries are 0? Then, of course, that would be a lot easier to work with. And you don't have to expand along rows. You can also expand along columns. So that formula is actually almost exactly the same. The only difference between this formula and this one is here, the index J is what is fixed, and we're summing over I going from 1 to n. So you can expand across rows or columns. In either case, you're choosing an element from that row or column and multiplying it by the determinant of a matrix of row I, column J removed. So we can expand across a row or down a column. Now, of course, in the cases of smallest matrices, you don't really have to think in terms of row or column expansion. You can just use relatively simple formulas. Like if you have a 1 by 1 matrix, the determinant of that is just the one element. If it's a 2 by 2 matrix that we've seen, you multiply the diagonal entries and then multiply the off diagonal entries together and subtract that. So these will come in handy when doing cofactor expansions across rows or down columns. Like if you have a 3 by 3 matrix to start with, you're going to be computing a few 2 by 2 determinants along the way. So that's what I'll get into with a problem. So I'll be able to show you how this process actually unfolds. And then we'll also, in this chapter, we'll learn about certain properties of determinant that will enable you to obtain them more easily. All right. So that's what I'll illustrate in this first problem. We need a determinant of this 3 by 3 matrix. So I'm just going to do a cofactor expansion across the first row. So this will be the default thing to do in most cases, unless you have a lot of zeros somewhere. So I'll show you like all the steps. Okay. So the determinant of this matrix, of a whole matrix, would involve this. First, we're going to go across this row. So we're going to taking the numbers 3, 5, and -6 and multiplying them by smaller determinants. So we start with a 3. We're going from left to right. And then this is a 1, 1 element. So then we strike out the first row and first column. So all of this is gone. And we're focusing on this matrix here. So you're going to take the determinant of that. So that's the first term. Then you move to the second element, a 5. Now notice I have a minus here, and that's because of this -1 to the I plus j power. Now I is always 1 in this problem. So then as j varies, you're taking -1 first to the second power, and third power, and fourth power. You're always going to alternate signs as you go across your row or column. So here we had a plus, here we have a minus. So this is the element in the first row, second column. So you strike out the first row, you strike out the second column, and that's what's left. So the 4, the 5, the 6, and the 3. That's this matrix right here. So that's the second term. And then we have one more. We move to the last element in the row, -6. And for that, so we have a plus sign, because so notice the pattern, plus, minus, plus, and then whatever the entry is. So now we're in the first row, third column. So you delete those, and you're left with this matrix, 4, 0, 6, 2. So you'll have a determinant of that. All right. So this is what the cofactor expansion across the first row gives you. So are there any questions about that before I continue? So what remains now is to take a determinant of each of these 2 by 2 matrices. And for that, we have the formula for determinant of 2 by 2. So we multiply the diagonal entries, so the 0 and a 3, minus the product of the off diagonal entries, the 5 and 2. So that's a determinant of this matrix. And then we proceed in the same manner with the rest of these. So 4 times 3 minus 5 times 6, and then 4 times 2 minus 0 times 6. And multiplied by the respective entries from the first row. So after that, now you're able to just carry out the arithmetic here and put everything together. And what we wind up with is 12. So that's the determinant of this matrix. All right. So you keep whittling it down to nice simple determinants like these 2x2s, and then use your cofactor expansion to see how to put everything together. All right. Now this next one, same idea, cofactor expansion, but and the thing is, all the problem asks for is the final answer. Actually, I'm going to preview. You can't see this because it's another window, but it's previewing the assignment. I'm pulling up this particular problem. And there's some choice in how you proceed. But all you have to enter is the final answer. You can get determined any way you like, but the point is to learn how to save yourself some computation. So what you want to do is find a row or column that has the most 0 entries to get the least amount of work. So in this case, we have a third row that has only one non-zero entry. So you can work with this 2 here and then delete that third row and first column where the 2 sits. And then you have this 3x3 matrix, 0, 0, 5, 8, 3 minus 2, 2, 1, 5, and then work with that. So we expand along the third row. Oops. Okay. All right, so we just take the 2 times what's left after we remove that third row first column. Now you have to be careful about the sign. There's a -1 raised to a power here, and it's raised to the I plus j power of the entry that you have in your expansion. So in this case, we have the entry in row 3, column 1. So we'll have a factor of -1 to the 3 plus 1, -1 to the 4th, but that's just going to be 1. So that's why we have a plus sign in this case. So if this had been the second row instead of the third, then we'd have -1 to the third power, so we'd need a minus here. So be mindful of that. So which entry you're expanding is -1. The ij entry that you have here, you need a factor of -1 to the I plus j. So now, so what we know from this expansion along the third row, your determinant is equal to 2 times the determinant of this matrix. I want to point out the notation here. Here we have vertical bars, whereas normally with matrices I have these square brackets. So this is a common notation for determinants. When you just have the absolute value bars, that's shorthand for determinant. So there's 2 ways you can write it, either by saying det and then of whatever matrix in square brackets, or you can just say absolute value and have a matrix entries, and that means the same thing. So they both mean determinant. So now that we've reduced the task of computing a determinant of this 4x4 matrix to a 3x3, we want to do the same thing. Find which row or column to expand along to save as much work as possible. And here we have an obvious choice, the first row, because it has only one non-zero entry. So let's see what we get from that. Okay. Oh. All right, so then we have 2 times a 5 that comes from here. And this is the entry in row 1, column 3. So we have a factor of -1 to the I plus j. That's -1 to the 1 plus 3, or -1 to the 4th. So that again will be a plus sign. So we have 2 times 5 times the determinant of a matrix you get by removing the first row and third column. So wherever 5 sits, that's the row and column that you remove. And what's left is 8, 3, 2, 1. Now we have this 2 by 2 matrix. Well, that you can just go ahead and work out directly. So we have 2 times 5 times the determinant of this. So we multiply the diagonal entries, multiply the off diagonal entries, and subtract. So 8 minus 6. So we get 2 times 5 times 2. So then 20 is the final result. So normally a 4 by 4, that'd be kind of a pain. Because you'd have to expand along some row or column and have as many as 4 3 by 3 determinants to compute. So then you're doing, this amount of work 4 times. But in this case, it was easier than that just because we have so many 0 entries that we can exploit by choosing the right row or column to expand along. And you're going to get the same result either way, and that's why in my labs you only have to enter a final answer, but at least we see a relatively quick way to get there. Questions on that one? Right. Here we have a determinant of a 3 by 3. Now, there's actually a trick that can be used for 3 by 3 determinants, and only 3 by 3. It does not apply for any other size matrix. But it's certainly a trick that's worth knowing. And it's called the Rule of Thrus. Sounds like something from Lord of the Rings. But anyway, what you do is you write down the matrix, and then you duplicate. After writing down columns 1, 2, 3, you repeat column 1, then column 2. And be sure to do it in that order. So columns 1, 2, 3, 1, 2. So then what you do to get the determinant with the 8 of these columns written off to the side is starting from here, where the 1, 1 entry, you write down all of the entries in the diagonal starting from here. So -2, 5, 0. So here we have a diagonal. And then here we have a next diagonal, 3, 1, 1. And then we have another diagonal, -5, 0, 4. And that's why these columns are repeated, so you can see what the diagonals are. So this way, so you multiply these, multiply these, multiply these, and those are added. So -2, 5, 0 plus 3, 1, 1 plus -5, 0, and 4. Then what you do is you then take diagonals going the other way. So starting from here, -5, 5, 1. So this diagonal. Then you go over to -2 and you do this diagonal. And then over to the 3 and do this diagonal. Those are multiplied and subtracted. So we have -5, 5, and 1. And then -2, 1, 4. And then -3, 0, 0. So add these diagonals going from upper left to lower right, and then subtract the diagonals that go from upper right to lower left. So that's the rule of Thrus. And once you work out all of those and add and subtract the appropriate diagonal products, we see that a couple of these are actually, in this case, this one, half of these are 0, so that's nice. So we just add up the remaining ones, and this is our result. So this is something you can do just for 3x3 matrices. It's kind of unusual that we have a trick that only works for that one case, but go figure. Now, the next problems deal with what happens when you perform row operations on a matrix, and how does that affect the determinant? Now, remember we have 3 different row operations. One is this one, where you take a multiple of a row and add it to another row. There's also interchanging rows, and then there's multiplying a row by a scalar, so scaling a row. And what do all those do to a determinant? So the nice thing is this operation of adding a multiple of one row to another. So in this case, what's happening here is I'm taking this row, the first row, 4, 6, multiplying it by k for whatever k is, and then adding it to the second row. And what we know is it doesn't change the determinant at all. That seems kind of strange that doing that much to a matrix would actually not change the determinant, but that's in fact the way it goes. Okay. So if you can recognize the matrix is being obtained from another by this kind of row operation, then you would know that the determinants of these 2 matrices are the same. All right. Here we have another row operation being performed. What we can see here is that this matrix comes from this one by swapping 2 rows. So that actually does change the determinant. If you interchange 2 rows of a matrix, it changes the sign. It negates the determinant. The row operation that I haven't covered in this, I'll just make a mention of it here. Scaling a row of a matrix by some constant factor c multiplies the determinant by c. So if I just take a first row and multiply it by 2, then that doubles the determinant. So this is how the 3 types of row operations affect the determinant. So no effect at all, changing sign for swapping, and scaling a row scales the determinant. And that comes into play in this next problem right here. What's happening here is we're taking not just a row, but the entire matrix and multiplying it by 4. So what does that do to the determinant? And this leads to a very common mistake that students make when it comes to determinants. So what's going to happen here is we just go ahead and compute these 2 determinants directly and see if they match. So first, we go ahead and work out 4a. So all that's happening here is I'm just multiplying 4 by this. So I multiply every single entry of a matrix by 4. So then we can just go ahead and take the determinant using a formula for determinant of a 2 by 2. So 32 times 8 minus 4 times 12. So we just work all that out, and this is what we get. We get 208. But on the other hand, what about this? Taking a determinant of A and multiplying it by 4. So that means taking a determinant of this, so 8 times 2 minus 1 times 3, and then multiplying that by 4, and we get 52. So these are not the same. So that's the conclusion. And so what we can say, though, is that determinant of 4 times A, in the case of a 2 by 2, it's 4 squared times the determinant of A. So, because notice we have a 208 here versus 52 here. Yeah, they're not the same, but we can also see they're off by a factor of 4. So here's what we could say in general. If you have a matrix A is n by n, then the determinant of a constant C times A is equal to C to the n times the determinant of A. Okay. So this is something to be very careful about, because sometimes students make a mistake thinking, okay, if you're multiplying the matrix by a scalar, that multiplies the determinant. No, but that's what happens if you multiply a single row by that scalar. If you're going to multiply, but CA is when you multiply every row by that scalar. That's why the factors stack up n times. So it's a very important property to keep in mind. Okay. Now here we have a geometric application of the determinant. So when you have a 2 by 2 matrix where the columns come from vectors that are describe the sides of a parallelogram. Okay, the determinant actually can be used to obtain the area of a parallelogram. So if you have two vectors u and v that define adjacent sides of a parallelogram, then you go ahead and put those vectors together in a matrix, u, v, or vu. Take the determinant, and then the absolute value of the determinant is the area of a parallelogram. And the absolute value is very important, because if you look at these matrices here and take the determinant of each one, well, this one is obtained by interchanging or swapping the columns of this matrix. Well, that's going to change the sign of a determinant. Of course, the area has to be positive. So these describe parallelograms that have the same area, they just are oriented differently. So the area that we get from these should be the same. So that's why we take the absolute value. And besides, determinants can be positive or negative. So we look at the determinants of uv. So here's u, and here's v. So then we go ahead and take the determinant. It's a times 0 minus c times b. So it's using a formula for a 2 by 2, and we get minus bc. But then if we go the other way, here we have vu. So then we have c times b minus a times 0, and we get bc. So predictably, we get determinants are negatives of one another, just because these two matrices are related by interchanging columns. So a parallelogram described by these adjacent sides is b times c. And it's interesting that the value of a ends up not playing a role in the area. But that's a result of the other side sitting on the x-axis. Okay. And since it's assumed here that B and C are positive, so we can say the area is BC. So now I'm going to show you a picture of this parallelogram. On the next page. Okay. So here we have this side right here. This is the vector u that has a x-coordinate of A and a y-coordinate of B. And then we have vector v. Oops, I forgot to label it. That has an x-coordinate of C and a y-coordinate of 0. And what we see here's a vector u, and the top and bottom are the same vector v. So this point right here is a vector u plus v. So that just defines this point, this vertex of the parallelogram. Now, I mentioned earlier that since the area turns out to be BC, we can kind of see why. Because if I were to draw a diagonal through a parallelogram, like from this point marked U to this point marked C, what we have is a triangle. And the triangle has a base of C, and the height is B. So the area of this triangle is 1/2 B times C. And really, the area of a parallelogram is just you could break it down into two triangles that each contribute half to the area. So so just as the area of a triangle is 1/2 base times height, area of a parallelogram is base times height. And since in this case the base times height can be determined solely from C for the base and B for the height, then that's that gives the area. So it's interesting so we can see from that why the value of A ends up not mattering. Okay, so questions about this application of determinants? Steve, a few people left in the meantime. All right. Well, for no questions, but I will stop the recording at this point, and the rest of you are free to scram.